So in the previous lectures, we have modeled the steel structure, we have modeled the RCC structure, we have assigned the specifications, and we have also assigned the properties also. So before moving on to further, I would like to fine tune this whole RCC and structural steel arrangement that we have modeled. First of all, we will check that whether some properties are missing for any type of member or not. So to do that, we need to go to select by missing attributes and by missing property. So here we can see that all of these structural steel members properties are missing. So we need to go to section database. Here we can select, let us say if we want to select the British and angle sections. So we need to select, let us say for example, if we want to select uniform angle 50-55, that is 50 is the flange dimension and 5 mm is the thickness. So we can select 50-55 and assign to all of these members here. After that, usually elevation bracings are double channel or box sections also, or back-to-back channels also. So we need to go to section database, British channel CH 125-65-15. Here we can either select back-to-back section or front-to-front section. So let us say in this example we want back-to-back section, so we'll have to click on add here, and then we assign the properties to all of these members here. So if we select this member, check that in 3D view, here we can see that now the members are here back to back. So here we can see that it is showing as I, that is both channels are now aligned as back to back. So after that, here we need to assign releases also, because it is a beam to beam connection. That is a tertiary beam is secondary beam is resting on the primary beam. So we need to select this beam here, and we need to go to specification and assign the releases. And RCC beam to column connection is most of the time moment connections only. So we left it as it is. Or if we want to do the fine tuning here also, then what we can do is that, as we can see that this member is going inside this column. So it's up to us that whether we want to assign offset command to this or not. So by right now, to make the thing short, we will skip this, or you can assign releases on your own for this member. Now the purpose of this lecture was basically to teach you about the supporting conditions that are available in this software. So when we go to general and support, here we can see that there are various options, that is no support, edit, create and delete. So when we left click on create, there are various type of foundations that are offered by the STAAD software. Number one is the fixed. Fixed is like the most used foundations. Pinned, only axial forces will be restrained, no moment will travel through the foundation. Fixed part is, let us say if we do not want the foundation to carry moment about the z-axis, so we can assign tick here, and there will no moment will be traveled about the z-axis. One more thing that I like to add here is that this is the global axis, not the local axis, as we are talking about the foundations. So enforced foundation, enforced butt foundation, multilinear spring, tension compression only springs, inclined and foundation. So for example, if we are designing a raft foundation in the STAAD software, so then in that case what we need to do is that we need to select reduction Y and enter the subgrid modulus here. So in our case, we are selecting it as fixed, and left click on assign to selected nodes and yes. So here we can see that we have assigned the fixed foundation to all the nodes. Or to, like just as an experimentation, what we can do is that we can add fixed also, and we can assign pinned foundation to this joint. Here we can see that the difference between the symbol of this is a pinned foundation symbol and this is a fixed foundation symbol. And similarly we can add fixed butt also. So let us say if we do not want any force about FZ and MZ, so here we can see that there is this fixity about the x-axis and y-axis. There is no fixity about the z-axis. So if we change it like that, so here we can see that both a moment about x-axis is also fixed and z-axis is also fixed. And if we change it like this, so here we can see that there will be vertical restraint about the y-axis, but there will not be any moment restraint. So usually this should be the condition. So the only moment taking a direction will be about the x-axis. So, and if any other type of like thing if we want to do, then we can add a fixed butt foundation like this. So in fixed butt foundation, the software clearly shows what exactly it is doing. So we have added various type of foundations. This is a fixed foundation. All three fx, fy, fz and mx, my, mz will show a value here. Only fx, fy, fz will show a value here. Mx, my, mz shall be 0. Only mx shall show a value here, and my and mz shall be 0. And for this, mx, my, mz shall be 0, as well as fz shall also be 0. So usually if you are a beginner to this fixed butt foundation, then it might take you some time to understand and grasp this concept, but this is a very simple concept, and it shall only be clear to you if you will practice a lot and you will study about what exactly, by applying various permutation and combinations and by checking the global axis simultaneously, then you can understand what exactly is being happening here. So in the previous lecture we have studied about the specifications, we have studied about the supports, we have studied how to assign the properties also. Now in this lecture we will study about the most important concept, that is loads and definitions. See, there are two concepts in the STAAD Pro for assigning loads. Number one is the definition, number two is the load cases. So basically there are some load cases. So before starting, we just need to left click here and then left click on add. Loading type we can add as dead, and we can name it as DL, that is dead load. Now left clicking here and then left clicking add again. So the thing that I was trying to say here was that wind definition here also, and wind load, snow definition and snow load, seismic definition and seismic load. So before we can assign snow load, we need to assign snow definitions. Before we can assign wind load, we need to assign wind definition. So here also you can see that it is not allowing us to add the wind load because wind definition is required in order to assign a wind load. Same is the case with the seismic loads also. So seismic definition is required in order to assign a seismic load. So if we want to add for example a brick wall load or a floor finishing load, then we can assign that, because that is like a static load that we can assign it from here only. But if we want to assign a seismic load, a time history load, or wind load, or snow load, so in those cases we do need to assign the definitions first. So for example, if we want to assign a wind definition here, so we need to left click here and then left click on add again, and then here we can see that we can assign the intensity and exposures, but these will be covered in detail in a separate lecture. In this lecture my purpose is to teach you how to assign all these loads, whichever we can assign. So first of all is the self weight. See, self weight of the structure is like the weight that will act due to the action of the gravity, and our vertical axis is y, so we need to select y here. Factor we can select it as -1.1. Let us say 10% we are adding it for the connections weight. So here we can see that there is this question mark coming. That is, the software is asking on which members we should assign this self weight. So we need to left click on assign to view, left click on assign and guess. So now we can see that self weight is now assigned to all the members here. After that we need to assign the nodal load also. So let us say on this node force of 500 kg, that is 5 kilonewton is acting, and Fy is from bottom to top, so we need to assign -5 here to act this load in the direction of gravity. Again this question mark is coming. Now as this is a nodal load, so we need to select the nodes here only. So here we can see that now assign to selected nodes option is now available here. So we can select these 4 nodes here and left click on assign to selected nodes and yes. So here we can see that 5 kilonewton load is acting on all these 4 nodes. And if we want to add a moment also, so let us say if we want to add a 2 kilonewton meter moment, so we can left click on change and yes. So now we have assigned moments also. So now self weight is clear to us, nodal load is clear to us. Support displacement we will cover that in a separate lecture, but now in this member load. So member load is also a very versatile option that is available, and it is like the most widely used option that we use it in the analysis of the structure. Number 1 is the uniform force. Number 2 is uniform moment, concentrated force, concentrated moment, linear varying trapezoidal hydrostatic, post-tensioning and pre-tensioning loads, and fixed end loading. So first of all, when you start with the uniform force loadings, here we can see that there is a small picture that is being shown as a preview of what exactly we are trying to do here. W1, that is the uniformly distributed load. So let us say we want to apply a UDL of 3 kilonewton per meter. Now there are various parameters, that is D1, D2 and D3. Now D1 is like when we don't want to assign a 3 kilonewton meter loading to the whole member, so we can assign it to a some part of the member. But before inputting any value here, I would like to go ahead with these values as 0 only, and this value is 3 kilonewton per meter. Now it is asking us about the direction, that is local axis or global axis. So if you want to assign the member load along the global axis, so we need to left click on add here and close. So let us say if we want to select these beams here. So left click on assign to select beams and yes. So now we can see that now the load is coming from bottom to top, which is an incorrect way. So we can add -3 here, and here we can see that now this load is acting in the direction of the gravity. Now if we select this particular, so for example, let us say if we want to study on this particular member, go to view and selected objects only, and left click on dead load, add member load. And here, if for example, if we want to add a load at a particular distance, let us say if we want to start this load after 500 mm distance, and left click on add. So here we can see that this loading is starting after 500 mm distance, and if we want to finish this loading at, let us say, 1 meter. So what exactly is happening here is that the length of the member is approximately 2 meter, and this loading is acting only on the 0.5 meter distance, that is 1 minus 0.5 meter. And if we want to shift this loading, let us say this UDL is not acting along this CG line or the center of gravity line. This loading is acting at minus 0.4 meter distance, that is some offset distance. So we can also change that, but that will not be shown in the 3D view. That effect we can only check in the analysis only. So if, for example, let us say if we want to increase it to 1.5 meter, so with this way we can assign like selective loading to a particular member. Now let us say select this member and go to view and selected objects only. So this was a uniform force. Similarly, we can apply the uniform moment also. So the uniform moment units are written as kilonewton meter per meter. So for example, if you want to assign a minus 3 kilonewton meter per meter moment, left click on add and close. So basically what is happening here is that the moment is being applied over the whole length, and if we change the units gx, so with this the things are more clear now, because here you can see that this is the global x-axis, and for global x-axis the moment is being applied here like this, and this is a uniform moment of minus 3 kilonewton meter per meter. And if we change the units, the axis like the direction will now change. So similarly we can select any other member for further studies. After that, if we want to apply concentrated force is like a single load will act on a particular member, so and at a specified distance. So if we want to apply, let us say minus 5 kilonewton, that 500 kg load in the direction of gravity and along the global y direction, left click on add and close. So here we can see that concentrated force is being applied on the center of the member. After that, we can select any other member again, and then we can study about the concentrated moment. So similar is the case with the concentrated moment also. So what we can do is that we can apply, let us say minus 6 kilonewton meter along the global x. So as we have selected uniform moment, similarly is the case with the concentrated moment, but the only difference is that it will apply on a particular point only, not along the whole length of the member. So here we can see this is the concentrated force which is being applied on the center. So similarly we can study about the linear varying. So in linear varying there are basically two types of loading that we can apply. One is a trapezoidal, second is a triangular loading. So if we want to apply trapezoidal loading, we need to select W1 and W2, that is the W1 is this value and W2 is this value. So let us say we want to change the W1 from 2 to 7, and direction shall be local only. Here it is not showing the global axis, so left click on add and close. And let us say if you want to apply loading to this member here, so changing the units. So now we can see that this is 2 and this is 7. So now some people might be thinking that why this direction is now from this is 2 and this is 7 while it should be 2 and it should be 7. The reason is the the member starting from this point to this point. And if we now there are two ways to switch the loading values. Either we can change this as 7 and this as 2, or we can go to select this member and we can go to tools and redefine incidence, and here we can select switch incidence of selected beams. So here we can see that now the loading is this is 2 and this is 7. So similarly we can select the W3 loading, that is triangular loading also. So let us say if we want a 10 kilonewton meter per meter loading, so we can select this member here and we can change the units here. So now we have applied a triangular loading in which this value is 10 kilonewton per meter and this value is 0 on the both ends. So this was the somewhat linearly varying, and this is also trapezoidal loading that we can apply in a much diversified manner. So in the previous lecture, we have learned how to apply the self-weight command, how to apply the concentrated load, uniformly distributed moment, concentrated moment, and trapezoidal loadings. So in this lecture, we will learn how to apply the flow loadings. So before studying the flow loadings, I just want to increase the size of the structure. So we can press translation repeat here. We don't need to select these particular members, because otherwise there will be duplicate members here. So number of steps as 3, default step spacing as 6 meter. Here we can see that the span of along this direction is 6 meter. We don't need to link steps and we don't need to renumbers bay, and we need to replicate the geometry as well as the property. So left click on OK. So with this option we have translation repeat the structure. Now if we want to apply the flow loadings here, flow loadings are for example, if we want to stimulate the RCC slab over which some loading needs to be kept. For example, maybe this whole area, that is from this point to this point, may be used for the stacking of the goods. So for stacking, maybe let's say the loading is in the range of 500 kg per meter square. So understand the things with greater clarity, we can separate this flow loadings here. So we can name it as flow load. Loading type we can select right now as none, because this is just for your clarity. And we can left click on view selected objects only. Now when we left click on add here, there is an option called flow load here in addition to the area load. Area load, I must say, it is not used in present RCC structures, but flow loading is the most widely used command. Here we can see that it is asking whether we want to add the flow loading along X range. X range means that parallel to X axis or Z or Y. Now this X, Z and Y is the global axis. Here we can see that whenever STAAD ask, it will point out that whether it is asking in the global or whether it is asking in the local. So we want to add, for example, the loading along in the direction of gravity. So we will enter global as Y, floor as Y range, pressure we can enter -5, that is 500 kg per meter square. After that it is asking Y range, X range and Z range. So what basically it means that we need to know the coordinate of this whole area. The coordinate of this is basically x0, y0 and z0. We just need to select the nodes cursor here and double click here. So along x-axis we need to apply the load from x0 to x24. So x minimum 0 and maximum is 24. After that, along z, you need to apply the loading from z0 to z5, because z5 is, and here also it shall be z5. So maximum 5 and y range. Y range is basically 0 here. So what we need to enter here is that we can enter -0.1 to +0.1. It means that whatever floor is in this range, that is -0.1 to +0.1, that is y0, the loading shall be applied. So we left click on add here, and here we can see that now the loading is applied. So this was just a simple exercise to explain you how to apply the flow loading in the direction of gravity. And if you will see this loading in the plan, here we can see that it is basically showing as the yield line distribution. If you don't know about the basics of this yield line theory of RCC slabs, it means that the software has distributed this area into two trapeziums and two triangles. So whatever shall be the area of this triangle and whatever loading shall be applied on anywhere on this triangle shall be transmitted to this beam. So if we will enter any data wrong, let us say if we enter floor X range here, so here you can see that the floor loading is not generated. Similar shall be the case for this, and here you can see that this is correct, but if you will enter the wrong sign here, it will be applicable from bottom to top. So if we want to apply the direction of gravity, we need to enter -5. And if we will enter, let us say sometimes it do happens that we just need the flow loading from this point to this point only. So we need to enter X here as 18 rather than 24. So here we can see that now the flow loading is applicable from 0 to 18 only. So changing back to 24. So here we can see that this is just a simple arrangement to apply the flow loading. So this is one type of option with one type of loading. Second, let us say if we want to apply flow loading on this area. So this is like an industrial steel structure here. So here what we can see is that the span is again 24. This is 5. We repeat the same procedure here. We enter the flow load here. Y range, pressure is minus, let us say 7.5, that is 750 kg per meter square. Y range for this is, we can select 4.9 to 5.1. That is our Y ranges between the range of 4.9 to 5.1. That is Y5. We can also select 4.8 also. So that is not like a rule that you need to enter -0.1 and +0.1 here. So X range shall be from 0 to 24 and Z range shall be from 0 to 5. Left click on add here. So here you can see that the flow loading is now generated here. So as you can see that the shapes is somewhat different here, and because why it is different, because it is also applying flow loading on the bracings also. We shall also study how to skip the loading on this bracing, because bracing is usually installed 150 mm below the industrial steel structure floor level. So that is why we don't apply flow loading on the plan bracings. But before that, I will like to add one more point here, that all these slabs, that is all these panels, are basically one-way slabs. That is, here you can see that the H by B ratio is basically 2. So it is basically one-way slab. So to model the loading for one-way slabs, what we need to do is that we need to enter one-way distribution here and select default as longer direction. So here we can see that now the loadings are only applied along the longer direction and no loadings are being applied on the shorter direction beams. And that should happen in the case of the one-way slabs. Now we will study the most important approach, or the option that I use most widely while modeling in the STAAD software, the group option. So what basically STAAD allows us, it allows us to make groups. So to access the groups, we can also find an option from this graphical user interface, or we can press Ctrl+G option on a keyboard. So we press Ctrl+G here, select type as flow, group name as 1. So left click on OK here. So here we can see that it is asking for creation of the group, and we can either associate to view, or we can manually select the all members. Or to make our work easier, what we can do here is that we can left click on select beams parallel to X, select beams parallel to Z. So here we can see that all the floor beams are selected here, but the plan bracings are not selected here, which should be our case. So left click on associate. So now we have defined a group with all the selected members here, and left click on add here, flow load, left click on group. Here we can see that this is the group that we have modeled, pressure as -5, and left click on one way distribution, that is longer direction. Left click on add here, and we can delete this group to see the arrangement here. So here we can see that now this loading is not applied on the bracing, unlike this option here. Unlike the previous option that we have just deleted, in that option what was basically happening was that the loading was also being applied on the bracing, but with this option we can skip the loading on the bracings. In this lecture we will learn how to apply flow loading for, let us say, wind loads. So wind load usually act in the horizontal direction. So let us say if we want to apply wind loading on these particular panels. So what we can do is that we can select flow load here and left click on add. So left click on flow load option here. Now we want to apply horizontal floor area load along x axis. So we need to select x range here. We need to apply, let us say, 1.2 kilonewton per meter square. Direction is global x. Now we want to apply the flow load along 5 meter by 10 meter area. So we need to know the coordinates here. So we can left click on this point here. So we need to apply x shall be from -0.1 to +0.1. Y range shall be from -5 to +5. And Z range shall be from 0 to 5. So left click on add here, and here we can see that the flow loading is only applied on the upper panel. So to apply loading on the lower panel also, what we can do here is that we can model a simple beam here. So if we change the loading patterns here, so here we can see that now the loading is applied on all the horizontal areas here. So similarly we can also apply flow loading on this particular panel also, but as like to transfer the loads correctly, we do need a horizontal member on the foundation level also. So this is just like an assurance that the loading shall be transmitted correctly here, because otherwise if this member is not available here, the loading for this triangular area shall not be distributed. So it is a necessity that if we are applying horizontal loads here, all the 4 sides of this loading generation should have floor beams. So until now we have learned how to apply the uniformly distributed load, concentrated loads, and flow loads. So after that, when we have applied the sample loadings, we can study about the materials also. So here we can see that basically isotropic and orthotropic 2D material option is available. So by default, steel, stainless steel, aluminum, and concrete materials are available in the STAAD software. So let us say if we want to apply the steel properties, steel material here, so we can just select all the steel members here and left click on assign to selected beams. So when we left click on edit here you can see that by default the yield stress of this steel material is 253,200 kilonewton per meter square. Tensile strength is 407800. Yield strength ratio RY is 1.5 and tensile strength is 1.2. That is editable. And this is basically the material properties. These are design properties and this is the material property. So in the material property here we can see that Young's modulus is 2 into 10 to the power 8 kilonewton per meter square, and Poisson ratio mu 0.3, density 76 kN per meter cube, thermal coefficient, critical damping, and shear modulus. This critical damping is a very important parameter. So when we are doing the dynamics, here we can see that the critical damping by default for steel material is 0.03, unlike in concrete where it is 0.05. So by default, when we are assigning the concrete materials, we are assigning the compressive strength of 27579 kN per meter square. So if we are using, let us say, M30, so we can add 30,000 here. And this is like material properties are fixed. So Young's modulus, Poisson ratio, density, thermal coefficient, critical damping, and shear modulus. And this critical damping, as I told you earlier also, that is a very important parameter. And we will also see when we are doing the dynamics how to make sure that either this damping is utilized while doing the dynamic analysis. So left click on OK here, and we can select all the concrete members here. Left click on assign to selected beams and gears. So here we can see that we have now assigned correctly all the material properties. And if we want to see that whether any material property is missing from some member or not, we can go to select by missing attributes and missing elasticity. And so now we have assigned the properties to all the structural steel members. Similarly, we can also create a material also. So type of material, let us say if we want to make a concrete section here. So as per your country codes, you can calculate the E, Poisson ratio, density, thermal coefficient, critical damping, and shear modulus values. And we can also enter the compressive strength. So all the experienced structural engineer, I must say, they do create a new material. Let us say if we are using M50 in the columns. So for M50, all these values shall be different, and the compressive strength shall also be different. So similarly, we can either edit these materials also. So by default, these 4 materials are available. Stainless steel is also available, and we can enter the design properties here. Let us say if we are using SS304 or SS316, so these properties are different for those widely used stainless steel sections. And we can also enter an orthotropic 2D property also. So this is just like the like the theoretical things that we do in the college. So to make the thing short, I'm repeating the concept here. That is, by default 4 materials are available: steel, stainless steel, aluminum, and concrete. If we are using high strength concrete, then we need to enter the compressive strength and all these values correctly here. And if we are using the software for the academic purposes, we can left click on create and enter the orthotropic 2D material properties. So this is the shear modulus along all the 3 directions: Poisson ratio, critical damping, density, thermal coefficient, Young's modulus, and Young's modulus along X and Young's modulus along Y, thermal coefficient along X and thermal coefficient along Y. So, and if we want to see that whether we have skipped assigning property to or skipped assigning material to any section, we can go to select by missing attributes and by missing elasticity or missing density, both. So now we have assigned the material also, we have assigned the loads also, we have assigned the supports also, specification also, and property also. One member that we have skipped assigning properties is this. So we can assign, let us say, 300 into 500 beam here. So now we have learned all these functions of the software. After that, we shall learn the analysis part also. So when we left click on analysis, 3 types of options are available here: preprint analysis and post-print analysis. So when we left click on preprint here, we have this define commands available here. So if we want the output to show the problem statistics, joint coordinates, member information, support information or solid information or element information. Then we need to, like, let us say if we want to know the joint coordinates of all the members and material properties of all the members. So here we can see that we can left click on assign to view, and again we can left click on assign to view. So this is basically the preprint, that is the options that can be accessed before the analysis, and after that the post print analysis. So here we are, after that, let us say if we want to know the joint displacement, member forces, support reactions, surface forces, CG, story drift, maximum force, cable sag, diaphragm center of rigidity, buckling shapes, physical member forces, element forces, member stresses, member section forces, and analysis results. So let us say if you want to print the support reactions, and if we want to print the member section forces. So this is basically just like to study deep further in the, that is about the various aspects of the structure. And if we will see the again the STAAD editor file here. So here we have joint coordinates also, member incidence also, we have the group definition also available here. We have this member release specifications also available here. The materials that are being used in this is basically number one is the isotropic steel, and second is the isotropic concrete. You can also change the grade of the concrete from here, that is from the editor file. And member properties, member offsets, the dead load which includes the self weight, and the flow loads here. And after that the preprint commands, that is print joint coordinates, list all. List all means that the whole structure. Print material properties, list all. Load list all. Print support reactions, and print member section forces, and finish. So we left click on save here and close this editor file. So in the previous lecture we have learned how to define the preprint and postprint commands. But when we are closing this editor file, it is showing some error. So what we need to do here is that the error was like the above line signal node, check possible syntax or typing error density lines. Actually we had deleted the parametric meshing of the slabs. So we do need to delete all this data here. So you just need to start here and up to here. You just need to either press delete option on your keyboard, as that data is a waste for us. So left click on save and close. So here we can see that we have this dead load and flow load commands here. So now we have defined the loadings also, supports also, specification, properties, materials, analysis command also. And one more thing that we do need to do in the STAAD is that we do need to write perform analysis. Either we can write perform analysis here, or we can go to analysis and we can left click on add here. So this is also a very useful option, that is either we do need to do p delta analysis, cable analysis, non-linear analysis, or pushover analysis, buckling, imperfection analysis. In our case we just need to do the simple analysis. So left click on analyze here and then left click on run analysis. It is showing us one error. No reference load case of type mass gravity dead life is defined for mass modeling. Center of mass calculation is not possible. Actually what happens is that when we are assigning the flow diaphragm, we do need to do the dynamic analysis only. So we can go back to the editor file here, and we can just simply delete the diaphragm command from the editor. So we press delete option on your keyboard, And now the whole analysis is performed, and STAAD is showing a 0 error, 1 warnings, and 5 nodes. So left click on done here. So we can left click on the STAAD output option. So here we can see that it is showing us the warning about the one-way loading. That is not an important warning. Actually what happens is that for some panels, this two-way and one-way load distribution panel becomes a warning. So it is also confirmed by the Bentley that you can ignore this warning. And after that, it is showing the tension compression converges after 3 iterations. Warning, it is shown that no section load locations have been provided, command ignored. That is, this command shall not be able to show us the output. Here we can see that it is showing us the support reactions as we had required in the preprint command. It is also showing us the material properties. Joint coordinates also it is showing us. And when we left click on post processing here, it asks us for which load cases we want to see the results. We can left click on apply and OK. So here when we left click on reactions here, the thing that I want to show you is that it was basically a pinned connection. So here we can see it is showing us fx also, fy also, and fz also. In this case, it will show us fx and fy also. It will not show us fz, and all the moments along all the axes shall be 0. For this particular joint, fx, fy, fz, mx, my, and mz, because this is a fixed joint. And for this, here you can see that it's also showing us the fixity about the x. So it will show us the mx. But it will show, the release was assigned for my and mz, so it will not show any value of my and mz. So for this fixed, all 6 values are being shown. For the pinned connection, only 3 values shall be shown. Mx, my, and mz shall be 0. And for this, we can see that only fx and fy shall be shown. Fx, mx, my, and mz all are 0. And after that, we can see the displacement also. Displacement, when we left click on summary here, in previously it is showing us the individual node numbers for all the load cases and all the displacements that are being happening in the structure. So when we left click on beam here, we can see the forces, stresses. For example, let us say if we select this column here, we can see the stresses, and it will also show us the graph. For example, let us say if we want to see the graph for this. So here we can see that this is the bending moment diagram, and it is showing us the fy value and it is showing us the fx value. Similar is the case with this column. And if we will see the BMD for this, so all these options are available with us. And if we want to see the MZ, so when we left click on this, we can see the bending moment along the major along the z-axis, and we can select the load case for which we want to see the bending moment along z-axis. And if we want to increase the scale of this bending moment diagram, we can right click here and left click on labels. Here we can go to scales, and result scale we can decrease the bending z value. So here we can see that automatically all the graph are being scaled up. So similarly, we can see the bending moment along the y-axis. This is basically the torsion. This is the shear along z, shear along y, and axial forces. So basically the red denotes compression and blue denotes the tension. So basically compression forces are being transferred to the columns. So now we have the purpose of this exercise was to just to make you familiar with all the options available in the STAAD. So this is not a final structure, or like this is just a theoretical structure that we have modeled and analyzed here. So consider it like a breakthrough project in which you have learned what are the basics of the STAAD Pro software and what shall we know, so that we can easily understand what I shall be teaching you in the next lectures. In this lecture, we will first of all model a monoslope roof, and then we will learn how to calculate the snow load on the top of that roof. So monoslope roof means that the slope is only along a single direction. It is not like truss or like the A shape that we see in our textbooks. So this is basically a monoslope roof, that is a single slope is available on the roof. So now this is basically concept of monoslope roof. How we can calculate the snow load on this roof is another concept. So either we can calculate that manually with the help of this American codes or Euro codes, but if we want to design a monoslope roof for a building in US, then you need to refer ASCE 07, and the latest version was released in recently in 2016. But if we want to know the snow load for, let us say, Chicago, so what we can do is that we can enter ATC hazards by location. So this hazards.atccouncil.org website will open. Left click here. So here we can see that 4 options are available, that is wind, snow, tornado or seismic. Left click on snow and enter the address here. As we want to know the snow load for Chicago, so we enter Chicago. So for Chicago, it is showing that as per ASCE 716, as I told you, the ground snow load that needs to be referred is 25 pound per square foot. LB means pound and SQFT means square foot. So if we want to convert 25 pound per square foot to kilonewton per meter square, we can enter. So 25 pound per square foot means 1.2 kilonewton per meter square approximately. So on the conservative side for Chicago, we can take the snow load as 1.2 kilonewton per meter square. But before that, we need to model a monoslope roof structure here. So keeping the thing simple, we will go to the editor and enter units, meter kilonewton, joint coordinates 1, 0, 0 and 0. Select the nodes cursor here, press Shift plus K option on a keyboard and press Ctrl C and Ctrl V and select the X as 6 meter. Again select both the nodes here and press Ctrl C, Ctrl V and Z as 5 meter. And select all the 4 nodes here and press translation and repeat. Now we can apply translation repeat on these 2 nodes only. Link steps, global direction is Y, default step spacing is 4 meter. And left click on OK. And after that we can select both of these nodes here, press translation and repeat, global direction is Y, default step spacing is 6 meter. Left click on link steps and OK. And go to add beam option here. So now we have modeled a simple monoslope roof here, and we can go to support conditions. Let us say we want to model pin supports. So left click on assign and OK. After that we can enter the properties here also, but before that I want to model secondary beams also here. For your better clarity, the total length of this is 5 meters, so we can right click here, left click on insert node, enter endpoints as 3. So the 1.25, 2.5 and 3.75. After that, go to geometry, add beam by perpendicular intersection. After that, we can go to specification also, left click on beam and release, start my and mz, beam end and my and mz. We can select all of these beams here, and we can assign the properties also. Let us say we want to enter the W sections, so we can enter W12 into 16 here. Left click on add here. Columns we can enter W12 into 16, and beams we can enter W6 into 15. Left click on add. So let us check that whether some property is missing or not. So we have assigned properties to all the members, and we have simultaneously we have assigned the material also. So now the thing started how we can calculate the snow load on this monoslope roof. So first of all, we need to go to this snow definition, left click on add, type number 1, ground snow load as 1.2 kilonewton per meter square, that we have calculated here. If you are using those American units, then pound per square feet option will be available here, and then simply you can enter 25 pound per square feet. Exposure factor we can enter as 1, thermal factor we can enter 1, and importance factor we can also enter as 1. Left click on add and close. So now we have defined a snow definition. After that, we can left click on load cases details here. First of all, we enter dead load here, that is self weight. Left click on add again here, and self weight we can enter in the direction of gravity, assign to view. After that, second load case we can define it as, left click on load cases detail here, left click on add, and then we can define a snow load here. So we can name it as snow, left click on add and close, and after that we can need to go to this snow load. So here it is showing that at least one floor group needs to be present. What it means is that we need to make this whole arrangement on which we want to calculate the snow load as a single group. So left click on press Ctrl plus G option on your keyboard, name the group name as group 1, left click on floor and OK, and associate to selected geometry. And then after that, if we will go to the same option again here, now you can see that option is open and floor group is number 1. Condition balanced as well as unbalanced. As it is a monoslope roof, the only option we are left is the balanced snow loadings. Define snow type, that is this one. So the definition is type 1. Roof type is monoslope. Roof obstruction is, we can select it as default. Let us say the roof slope factor for this as per the slope is in the range of 0.85. So left click on add here. So now we have defined a snow loading here also, and after that we can add a perform analysis, and then we can go to analyze and run analysis. So we go to the output file, so it is also showing us the instability at joint number 13. So what we can do is that we can assign a fixed support here. Let us say 2 joints are fixed and 2 joints are pinned. So now we can see that all the warnings are now removed. And after that, when we click on the STAAD output option here and scroll down, we will see that the snow load generation has been performed as per ASCE 2002. So if you will use the latest STAAD Connect version software, and then in that software the snow load generation shall be as per the ASCE 2016 only. So if we will see the calculations here, you will see that exposure factor we have entered as 1, thermal factor we had entered as 1, importance factor 1, ground snow load is coming out to be approximately 25 pound per square foot, and minimum snow load on flat roof is 0. So snow load on flat roof is 17.543. Roof slope factor is 0.793. Balanced snow load is 13.91762 pound per square foot. So all the calculations have been performed as per the ASCE 2002 as per the snow load definition that we had given. So in the previous lecture we have learned how to generate snow loading for this monoslope roof. So in this lecture I will try to teach you how to generate snow loading for an gable roof and how to generate unbalanced snow roof loading. So for that we first of all we need to model a gable roof. So we go to view from +Y option, select all the beams here, and then select the mirror option here. So our plane is along the YZ, so we need to select mirror plane as YZ and node on plane as this. So we need to copy this whole arrangement and then left click on OK. So now we have drawn a gable roof, and after that we need to go to general load and definition here. We need to select self weight for the whole structure. And in the previous example we have generated this balanced snow roof loading here, and we need to rename it as snow balanced. And we need to add another load case here, snow unbalanced. Left click on add here and then close. So for this we have added this floor group as 1, condition as balanced, defined snow type as 1, roof type as mono, and roof obstruction as default. We can select as obstructed here for this, and roof slope factor as 0. So one thing that you should always check, that press Ctrl+G option on your keyboard to check that what is the floor group definition here. So we select this, left click here and then left click on highlight. So we need to name two groups here, one for the left and one for the right. So we select all the beams here and then left click on associate. So here we have assigned the one to the left side roof. So after that we need to left click on create here, and then we can left click on 2 option, that is we will name this group as 2. So left click on OK, go to view from +Z, select all the beams here and then left click on associate. So now we have named 2 as this group and 1 as this group. So left click on close here, and then you need to left click on snow balanced and then left click on add here. So left click on snow load option. Here for the balanced we need to select the balanced option here, and then we need to left click on 2. As we have already generated the balanced snow load for the left side, similarly we need to generate the balanced snow load for the right hand side also. So roof type we need to select it as mono for this option here, and roof obstruction is obstructed and roof slope factor as 0. Then left click on add here. After that we need to generate an unbalanced snow load. So but to generate the snow load correctly, on the left we will select the option balanced only, roof type as gable, and roof obstruction is obstructed, and roof slope factor as 0. And in the second snow load generation, when we select as 2 here, condition as we need to select as unbalanced, and roof type as Gable, and roof obstruction as obstructed, and roof slope factor as 0. So this is the condition that can depends on your particular model or particular design requirements. So for this load case, I am selecting these options. So now we have generated these two loadings, that is snow balanced and snow unbalanced loading. And after that, we need to left click on analyze and run analysis, and then left click on done here, and then we need to open the STAAD output option here. When we go to the end of the analysis report, you will see that there are 4 types of data that is available. First one is the balanced no loading generation, that is both balanced no load is same. And in the second option, we will see that balanced no load is 5.263 and unbalanced no load is 30.24654 PSF, that is pound per square foot. You need to notice that we are using the units as SI, but the loading that will be generated here shall be always be in PSF, that is pound per square foot, or it shall always be in American units. So we can also select the plane here, go to view and select objects only, go to view from +Z, and then we can select the bending moments also here, that is bending Z moment. And then we can go to post processing, left click on OK here. We can select beam here and left click on labels, scales, left click on apply immediately, and then decrease this bending Z scale. So now we can see the bending moment diagram clearly. After that, we can go to results, view value, beam results, bending as maximum, and annotate, and then close. So here we can see that on the left, for the snow unbalanced no loading condition, it is minus 0.7 on the left and minus 4.02 km on the right. Whereas for the snow balanced, both the sides are equal, that is minus 2.333 km for the left also as well as for the right also. So this is the thing that you should understand, and always do the manual calculations also before doing the final analysis. And there is one more thing that you should know, that is if you are conversant with the ASCE 07 2016 code, the W, that is the width of the portal that needs to be considered. As per the ASCE, the W value should be from this point to this point, but as per the STAAD, the W that STAAD considers is this value, that is 6.325. So if you will cross check your results manually with the generated snow loading here, there shall be some difference, and that is the snow loading that shall be generated here shall always be somewhat on the higher side than what you will calculate manually. The only reason is this, because it will STAAD will calculate the W from this point to this point, but as per the ASCE, that is manual calculation, the people usually calculate from this point to this point. So with this lecture, I hope you have now understood how to calculate the snow loading correctly with the help of STAAD. And in the next lecture, we will learn how STAAD generates the wind load and how we can easily generate the wind load for various type of structures. In this lecture, we will learn about the frequency determination of a structure. Now, why we are talking about the frequency of a structure when we are talking about the wind load generation? So in the general load and definition option, in the definition you will see that there is an option called wind definition. Left click on add here, and then again left click on add and close, and then again left click on add here, and then there's an option called calculate as per ASCE 07. So when we left click here, you will see that there's a proforma for generating the wind loads as per the American standards. So there as per the STAAD Pro Select Series 6 version, there are 3 ASCE codes available, that is 1995, 2002 and 2010. In the latest Connect edition, there is also the latest code for ASCE 07, that is 2016. So if in the STAAD Pro, you can generate wind load for building structures, chimney, tank and similar structures, solid signs, open signs, lattice framework and truss tower. So considering as a trial option here, left click on main building data here or truss tower data here. You will see that there is an option called structure natural frequency. So now it is a structural engineer job to calculate the natural frequency of a structure. It is not like when we are talking about the truss tower, then only we are talking about the natural frequency. Even if we select the building structures here, then even you will see that in the main building data, it will talk about the building natural frequency. So how we can generate this building natural frequency? There are various options that are with a structural engineer to calculate this building natural frequency. Number one option is the code itself guides us how to calculate the rough natural frequency of a structure. That is ASCE 07 code has various guidelines about calculating this building natural frequency. It is not like if you don't have STAAD, you cannot calculate the natural frequency of a structure. So considering this natural frequency option, I will like to share various other knowledge database that is available on the internet about this frequency. So before that, I will like to add one more thing here, that is left click on load case detail here, left click on add here, generate this load case 1 and then left click again on add. Here you will see that STAAD has an option called frequency here. That is, there are two types of frequency that can be generated by STAAD Pro. Number one is the Rayleigh frequency. Number two is the modal calculation. Rayleigh frequency is just like a static part of the structural analysis. So, but modal calculation is like the dynamic part of the structural analysis, and it will calculate the frequency for all the modes. But Rayleigh frequency is just like a static natural frequency of the structure. But for simple structure, Rayleigh frequency is more or less equal to this option here. That is, both of these options generate more or less as same natural frequency of the structure. So before we learn how to calculate the frequency of the structure by this, we should learn what exactly do you mean by the Rayleigh frequency. There must be many people who are not somewhat confident with the Rayleigh frequency concept. So there is this beautiful article written by Mr. Attilio Andrade on the Bentley community forum. He has very beautifully explained what exactly do you mean by the Rayleigh frequency and how you can calculate it manually also. So he is saying that Rayleigh method is basically the method based on the energy conservation. How we can say that energy conservation? That is, energy remains constant. What two types of energy we are talking about? Kinetic energy and elastic energy. So the basic concept of the Rayleigh method is that during the oscillation of the structure or of the system, the sum of the kinetic energy and elastic energy remains constant. That is, when kinetic energy rises, elastic energy somewhat decreases, or what we can say is that when kinetic energy is the maximum, elastic energy is 0, or when kinetic energy is 0, elastic energy is the maximum. So what we can say here is that the formula for kinetic energy is basically half of sigma mi into vi square, and the formula for calculating elastic energy is half of sigma of fi into yi. So that is the force into displacement. So what we need to do here is that we need to equate both of these. That is, half of sigma mi vi square. This is nothing but half kinetic energy is equal to half mv square, what we used to learn in the school also. That is half of f into x. So this is basically a simple diagram here, that is we are lumping 4 masses here, m1, m2, m3, and similarly it goes up to mn. Fn we apply here, f2, f3 and fn here, y1, y2, y3 and yn. So this method is basically used to obtain the approximate frequency of first mode of vibration. Then the frequency to be determined is W1 and displacement is similar to the first node. So summing up all the things that have been explained here, Fi is nothing but Fi into Hi divided by sigma of Fi into Hi, and Fi is nothing but Mi into G, that is distribution of forces having a linear deformation. So the basic formula for calculating W1, that is Rayleigh frequency, is 1 upon 2 pi sigma of Fi into Wi divided by sigma of Mi into Yi square, and that needs to be square root, that is 1 by 2. So he has also attached this simple example, that is he has modeled a simple column of this 8 meter height and a concentrated weight of 10 kilonewton on all 3 levels. The column size that he has taken is 200 into 400 mm. So STAAD calculated the Rayleigh frequency of the structure to be around 2.48 cycles per second, that is CPS. And when he is calculating all the data manually here, that is Fi is equal to Wi into Hi divided by sigma Wi into Hi, and then he puts the formula here, that is 1 upon 2 pi sigma Fi into W divided by sigma Mi into Yi square. Then also the frequency that he is calculating is approximately 2.477 against 2.484 by STAAD Pro software. So he has basically entered the Wi values here, Mi values here, Hi values here, that is height. Then he has calculated the Fi, Yi, Fi into Yi and Mi into Yi square. So with this method he has calculated the frequency with the help of this formula. So this was just an formula introduction to the Rayleigh frequency, that is this is the basic formula that is being used by the STAAD Pro software for calculating the Rayleigh frequency. There is one more article that is available on the internet free of cost regarding the Rayleigh frequency on the Structural Engineering Forum of India website. So he has said that Rayleigh frequency derives natural frequency of a structure by equating potential energy and kinetic energy. The thing that he has also explained here, that is kinetic energy is equal to elastic energy, or elastic energy also means potential energy. You don't need to get confused here. So for a simple cantilever beam, the point could be the tip of a cantilever, and for a multi-story building there can be various points on all the floor levels. So this is the same equation that he is using here. So there is this another explanation of Rayleigh frequency by Mr. Manohar here. He is saying that it is basically a quick way to estimate the fundamental natural frequency, and starting with crude approximation, that is rough approximation to the mode shape. So if one needs to estimate the fundamental natural frequency of a cantilever beam, he can use the deflected profile of the beam under self-weight also as an approximation to the mode shape, and arrive at an approximation to the first natural frequency using the approximation expression square root of u into ku divided by u into mu, where u is the assumed mode shape, u star is its transpose, and k and m are the structure mass and stiffness matrices respectively. So this is the most important line here, that is true natural frequency of the structure shall always be less than the natural frequency that we shall calculate here. So it will always be, the Rayleigh frequency shall always be on the conservative side, as it is always less than the true natural frequency of the structure. And this is the simple example that he is explaining about the natural frequency of the structure and Rayleigh frequency. So imagine two postures of a soldier. Okay, so for a soldier there are two postures. One is the true attention pose, that is the stand in attention here, and second is the stand at ease posture here. So to stand in attention, the soldier need to stiffen his body, which will naturally leads to enhanced natural frequency. So similarly, an approximation to the mode shape that is different from the true mode shape, additional node forces need to be applied to maintain the assumed shape. So what basically he's trying to say here is that the standing at ease posture and standing in attention. So the standing at ease is the true normal mode, and stand in attention is an approximation. So stand in attention is a Rayleigh frequency, and stand at ease posture is the true natural frequency of the structure. So you need to understand that the structure also we are classifying it as two natural frequencies. One is the Rayleigh frequency, that is just an approximation here, and second is a true natural frequency of the structure. So I will attach the PDF of both of these websites for your easy reference. I must say that I am not the writer of these two articles. These two articles belongs to Mr. Attilo Andrade and Mr. Manohar here. So coming back to our software here, that is we can now calculate the Rayleigh frequency and model calculation method. But before that, I will like to model a basic structure for our easy calculation and understanding how to calculate the frequency of a structure. So we can open the STAAD editor here. Enter the joint coordinates. Press Ctrl C plus Ctrl V on your keyboard to just copy paste here, and then left click on Y as 5 meter, and then left click on OK. Select both the nodes here, and then left click on translational repeat here. Left click on select X, and default step spacing is 6 meter, and then left click on link steps here. So draw left click on add beam option here. Go to view from plus Z, and then select this cursor here, and then again go to translational repeat option here, and then enter the default step spacing is 5 meter, and then left click on link steps option here. So now we have drawn a simple frame for calculation of the frequency. So we can delete this beam here. Go to supports option here, and then left click on create. Select the fixed option, left click on add, and select both the nodes here, and then assign. So we need to go to now load and definition option here. Left click on load case detail. Enter two types of load cases, that is dead load and live load. Left click on dead load, and then left click on add here again. Select the self fit option. After that, enter member load here, and then enter uniform force as minus 6 kN per meter. Direction as global Y. Select both the beams here. So now we have applied the dead load in the direction of gravity here. Similarly, we can also enter live load here, minus 5. Select both the beams here by pressing Ctrl option on your keyboard, and select assign the property here also. Left click on section database. We can enter general sections here, Let us say we enter UB 203 into 133 into 30. Left click on add and close here. Select all the beams to be of same size. Left click on analysis. Left click on add and close. So now we have entered properties also, supports also, loads also. So the thing that I am trying to convey to you is that if we are talking about the natural frequency of the structure, the loading along the Y direction is not sufficient. We need to enter the loading along global X direction or global Z direction. That is, we need to enter the horizontal loadings also. And before that, we can left click on this dead load option here. Left click on add here. As a trial and error method, let us instruct the STAAD to calculate the Rayleigh frequency. Left click on add and close. You will see that the calculate Rayleigh frequency option is now available here. Left click on analyze and run analysis. So going to the output file. So STAAD has calculated the Rayleigh frequency of the structure to be 51 cycle per second. But you need to understand that the thing that I was trying to convey you initially, that the loading that we had applied is in the Y direction. So the displacement that shall be happening shall be in the Y direction. But for wind loading, we need to calculate the horizontal frequency of the structure. So we need to enter the horizontal loadings here. So we need to delete the vertical loadings here. And we can delete this load case also. And then left click on DL. Then left click on nodal load. And let us say we apply 10 kilonewton, that is 1 ton loading on the nodes. Select the nodes cursor here and then select both of these nodes here. So now we have applied the loading along the horizontal direction. So the displacement that shall be occurring shall also be in the horizontal direction. But this system is not correct. That is, fx 10 km should be above the calculate Rayleigh frequency option. So we select these, press Ctrl X on your keyboard and press Ctrl V again. So now the system is correct. And after that, when we left click on analyze and analysis, and then again we go to the calculation. So here we can see that this is the practical value that we are getting. That is, the frequency of our loading one is 2.25 cycles per second against the 50 cycle very high frequency of 50 CPS for the gravity loadings. So instead of calculate Rayleigh frequency, what if we calculate the input the model calculation? So we left click on model calculation here, left click on add, and then left click on analyze and analysis. So here you need to understand that this was the Rayleigh frequency for loading one. Rayleigh frequency is approximately 2.25 cycles per second. And when we are checking the model calculation here you will see that for the mode 1 it is 2.240 CPS, that is cycle per second. So against a model calculation which is calculating 2.240 CPS, Rayleigh frequency is approximately 2.252. So there is minor difference between the Rayleigh frequency and model calculation, but they are more or less similar. So this is the frequency that we need to enter in the wind load definition. So first of all, when we are calculating the wind load automatically for a structure, we need to first of all calculate the Rayleigh frequency and model calculation and then assign all the correct data to the wind definition here. So I hope you are now having the clear idea about what exactly do you mean by Rayleigh frequency, what exactly do you mean by model calculation, and what are the relation between the Rayleigh frequency and model calculation. That is, both of them are almost or more or less same. and what is the significance of calculating the frequency also. And when we are designing the dynamic foundations also in the STAAD Pro, then even I use this Rayleigh frequency or modal calculation option to assess the vibration of the structure and to design the foundation so that the foundations are not in the same frequency as the equipment that we are setting upon that foundation. So in the previous lecture, we have learned what are the basic concepts of Rayleigh frequency, modal calculation, how we can calculate the frequency, natural frequency of a structure. And in this lecture, we will try to model a truss tower, and then we can check how STAAD calculates the wind load on a particular structure automatically. So first of all, we need to model a truss tower. So we go to editor file here, and then we enter the units, left click on joint coordinates, enter the joint coordinates as 1, 0, 0 and 0. Press Shift plus K option on your keyboard. Let us assume the truss tower bottom spacing is at approximately 10 meters along both the directions. To make the things clear, we can model a beam here. Select both the beams here, go to geometry, intersect selected members and intersect. Now we have got a center point as a node here. Let us assume the height of the truss tower is approximately 50 meters. So what we can do here is that press Ctrl C, Ctrl V option on your keyboard and select X as 2 and Z as -2. Press Z as 4 meter. That is what we are doing here is that we are assuming that the 10 meter by 10 meter is approximately reducing to 4 meter by 4 meter on the top. This is just an imaginary or hypothetical truss tower. So now we can model the beams here also, so for our clarity, and copy this node on the top as Y as, let us say, 3 meters. So we can make the apex here like this. And left click on add beam option here. Left click on this beam and left click on insert node. The height of the length of this beam is approximately 50 meters. So what we can do is that we can divide this length into 10 parts. That is, left click on add endpoints and then left click on OK. Similarly, we can add endpoints here also. So select these beams and left click on insert node, go to N as 10 and then go to add beam option here. So now we have made a simple tower here, and then we can add the diagonals here also. So now we have made a simple tower here, and we can also add a double bracing on the bottom if we want. Similarly, we can draw an offset here also. Draw a cross beam here so that we can have the midpoint. Go to geometry, intersect selected members and intersect. Now we have got this node. So that we can draw a connection like this. I am making this example just to have, it's like you can easily practice on this, as it is the truss towers are somewhat complicated to model. So if you can model this type of structure, you can easily model anything else on the STAAD software. So now if we will do the work smartly, then we can just like mirror this new structure about this. So what we can do is that we can select the beam cursor here, and then left click on insert node, add midpoint. So this node will act as a reference for the mirror generation. So left click on generate mirror here, mirror plane as XY, mirror plane shall be XY, and the node plane position shall be this, and then left click on copy. So here we can see that we have just copied this whole arrangement about the center point, and after that we need to merge this member, as we don't want a node here. Go to geometry, merge selected members and merge. So now we have modeled a simple truss tower structure, and after that what we can do is that we need to go to support, left click on create, fixed, left click on add, go to view from +Z, and then left click on assign. After that we can go to property, section database, go to go to American, left click on angle here. We can select 100, 112 angle here, L, and then left click on add and close. So just for a shortcut, what we can do is that we can assign the members here. So select Indian, then left click on angle here. We can select ISA 75/75/6 for our truss tower. Then left click on add and close. We can left click on assign to view, and then we can check the 3D rendered view here. So here we can see that ISA 75/75/6 angle is assigned to the whole truss tower structure here. And coming to the basic purpose of this lecture, we need to go to definition and then left click on wind definition, then left click on add, and then again left click on add here. Here we can select the calculate as per ASCE 7. So here we can select the truss tower. So we need to know the exposure category, basic wind speed, building classification category. After that, what we need to know is the truss tower data. That is, what is the height of the truss tower, what is the width, ratio of solid area to gross area of the tower face, horizontal cross section, that is triangular or square, structure natural frequency we need to know, and structural damping ratio. We also need to know that. So after that, it will calculate the design pressure values. So coming back to our structure, the height of the truss tower is approximately in the range of 53 meter, and the frequency we need to know. So we can left click on add here, left click on dead load, then again left click on self weight y as -1. After that, let us say there are some loadings on this point and this point of, let us say, 5 kilonewton. So we need to enter Fy as -5. We need to select this node and this node here, and then left click on assign to selected nodes and yes. So now the thing is, whatever loading that is acting on this structure, let us say 5 kN is loading is acting on these both of these 2 points. So if we want to calculate the frequency of the structure, let us say we go with the Rayleigh frequency only. So we need to enter this value in the X category if we want to calculate the frequency along the X direction. And we need to select the analysis, that is perform analysis command. We need to check whether we are missing any property, and then after that we need to left click on and analyze and analysis. There is an error here. We need to delete this command and then again analyze. So if we check the natural frequency of the structure, it is approximately coming out to be 2.40157, or we can say 2.402 cycle per second. So coming back to the wind definition, left click on add, left click on calculate as per ASCE, building classification category, that we can select it as 2. Basic wind speed we can set it as 140 miles per hour. Exposure category, let us say we select it as B, And building structures, we can select it as lattice or truss tower. And this exposure and this building classification category, both of these are given in the ASCE 07. So for this type of structure, we can go with building classification category 2 and exposure category as B. And left click on apply. So both of this data change, and now this is truss tower data. So height, we can enter it as meter, as approximately 50, we can say 55 meters. Width as approximately meter is, we can enter it as approximately 10 meters. Ratio of solid to gross cross section here, we can select it as 40. Horizontal cross section is square. Structure nature, we can see as 2.40157. And structural damping ratio for steel, we can select it as 0.05, and then left click on apply. So now the STAAD has generated this graph here. And after that, if we will go to design pressure for other structure, here you can see that G value, it is automatically being calculated as 0.85 and CF as 2.28. And this is the table that has been generated for our structure. And like in snow loading, the generation was in US units, that is foot and pound per square foot. And so for this wind load also, the unit shall be pound and foot only. And then left click on apply and OK. So now the units that were in foot and pound per square foot in that window, now it is automatically converted to the kilonewton per meter square and height. And then left click on add, select the factor as 1. By default, the STAAD takes the factor as 1 only. We can left click on assign to view. And after that, we can select the load case detail, and then we can enter the wind, that is WLX and WLZ. Left click on add here. So if we were talking about the X direction here, so this is basically the windward frame, that is this frame is the windward if we are talking about the wind that is blowing from this direction, and this on the back is the leeward frame. So on the windward frame, what we can do is that we can left click on WLX, we can select wind load, windward phase factor, we can set it as 0.75. that is remaining 25% will act on the leeward frame. Left click on open structure, and we can select the X range as from 0 to 3, Y range as 0 to 50, and Z range as 0 to 10. Left click on add here. So now we can see that the structure has now turned to blue. Or what we can do is that we can change the height of Y to 53. So now we can see that the whole height of the tower has been considered, although the wind load is not being generated on the top here on this frame. And if we want to study clearly what exactly are these blue lines, we can go to labels, scales, apply immediately, and we decrease the value of this. So here we can see that the STAAD has calculated the wind loads in the form of UDL that shall be applied on these members here. And if we want to see basically what are the values that has been calculated, because we cannot just trust blindly about these blue lines. So what we can do is that, let us say if we want to check the loading on these 4 members. So we select these 4 members here, go to view selected objects only, and go to labels. And here we can see that there is an option to display load values. So left click on apply. So here we can see that the STAAD is now giving us the value that has been generated as per the this particular angle and this particular intensity of wind load. So whatever it is written in the golden color, this is the value of the wind load that has been generated. So we can press Shift plus V option on a keyboard to switch off the values. Similarly, we need to apply the loading on the levered frame also. So we enter the factor as 0.25 and we need to enter the range here also. That is from x7 to x10, and y range we can enter it as 0 to 53 and z range is 0 to 10, and then left click on open structure and then left click on add here. So now we have basically assigned the wind loads for windward as well as for leeward frame. That is 0.75 factor has been assigned here and 0.25 factor has been assigned here. And you must be wondering why we are not able to assign wind load on this particular part. So what we can do here is that basically the x range that we have assigned does not comes up to this point. So we can increase the x range to x equal to 5 meter and then left click on change. So now we can see that now the loading are being applied on the top members also. Similarly for this we need to select x minimum range as 5. So now we can see that the load has been generated correctly. But load also needs to be applied on these particular members. So we can select the range of Z as minus 3.5 to plus 13.5, minus 4 to 14. So now the loading is generated on these particular members also and on the levered frame also. Similarly, we can generate the wind load for Z direction also. Like we have calculated the wind load and assigned for the X direction. Similarly, we can assign a frequency or like UDL for loading along the Z direction also, and then we can calculate the frequency. And similarly, we need to generate the different type of wind load, that is wind along Z. As this is a symmetrical structure, so the frequency must be same along both the direction. But in some structure, the frequency may not be same along both the directions. So for that, what we need to do is that we need to calculate the frequency for both the sides, and then we need to calculate the wind force and wind intensity along both the sides. And the same procedure we need to repeat for WLZ also. So this can be considered as your assignment. That is, you can calculate the frequency along Z direction. Similarly, you can enter the loading for the WLZ also. So the purpose of this lecture was just to give you a clear-cut idea of what exactly is the procedure to enable the software to calculate the wind load manually for open trussed tower. So in the previous lecture, we have learned how to determine the frequency of a structure, how to apply the automatic wind load as per the American standards, that is ASCE 2010. So in this lecture, we will learn how to model a simple RCC building and how to calculate wind load for a normal RCC building. So first of all, I would like to read some points from the American Standard Code itself, that is ASCE. The ASCE code guides us that the gust factor gust effect factor for a rigid building is permitted to be taken as 0.85. That is the value of G that we will see in the STAAD tutorial. The other most important clauses are these three clauses. That is for structural steel moment resisting frames, NA. That is approximate natural frequency, or we can say approximate lower bound natural frequency in Hertz. The course has given us the guidelines for the sample calculation. Like if we want to apply the wind or calculate the wind load manually also, then it's not like you need to calculate the Rayleigh frequency or you need to calculate the Modal frequency. You can just put the height of the building or structure here, and then you can calculate the natural frequency. The first formula is for structural steel moment resisting frame buildings. That is the normal steel structures that we usually use in the industrial structures. For concrete moment resisting frame buildings, that is the hospital structures or some commercial building structures or residential building structures. For that, the frequency is 43.5 divided by height of the structure to the power of 0.9. And for structural steel and concrete buildings with other lateral force resisting systems, the approximate lower bound natural frequency is 75 divided by H. So the code guides us for various type of buildings, the different values of the natural frequency that we can automatically take. And for concrete or masonry shear wall buildings also, it is permitted to use Na is equal to 385 Cw to the power 0.5 divided by H, and the value of Cw is given by this equation. So for rigid buildings or other structures, it is guiding us about the gust factor also, whereas normally usually in structures, I also in my office I take it the value of G is 0.85 only for low rise buildings and for the normal structures. If we are doing some very special structures or very unsymmetrical buildings, then we need to calculate the value of G. And most of the times, if we are doing very unsymmetrical buildings, special buildings, we usually go by the wind tunnel test report. And all these parameters are specifically explained in the wind tunnel test report itself. And this is the very important table that you should know. That is main wind force resisting system. It is also known in short form as MWFRS. If you will see the textbooks as per the American standards, or if you are working in the office, then the term used mostly by the engineers is MWFRS, that is main wind force resisting systems. And the internal pressure coefficient, GCPI, you should notice that we are not talking about the CPI. Like if you are conversion with the Indian standards or if you are conversion with the British standards, then only CPI term is used. But right now, for American standard, we will always use the term G into CPI. STAAD also itself, in its various options, ask about the option GCPI. So there are mostly three types of structures all over the world in all different standards. Let it be European, American or Indian standards. They always talk about three types of this openings: enclosed, partially open, and open buildings. So for enclosed, partially enclosed, the value of G into CPI is plus minus 0.18. For partially enclosed, it is plus minus 0.55. For partially open, it is plus minus 0.18. And for open building, the G into CPI is 0. Obviously, if the building is 100% open, then there's no scope of developing the suction from the inside. And how we can decide whether the building is enclosed or partially enclosed? With the help of this formula, that is A0 is less than smaller of 0.01 Ag, and or 4 square feet, and AOI divided by AGI less than 0.2. So all these terms are specifically explained itself in the code itself. So I will like you to study the code carefully and remember all these terms, and if possible remember this table also. That is plus minus 0.18 for enclosed and partially open, and for partially enclosed building it is plus minus 0.55, and for open building it is 0. So coming back to the STAAD, so the purpose of this lecture is to make you familiar with the American standard natural frequency and the how American standard guides us about the GCPI value, and how we can calculate automatically the wind forces on the simple RCC buildings as per American standards. The code which I am showing you here is ASCE 2016, but in the older version of STAAD, except in the Connect edition, it is showing the option of ASCE 7 2016. But in the up to select series 6, it only shows us the option of ASCE 7 2010 only. So in this lecture, I will model a basic RCC building, and then we can calculate the natural frequency as per this formula, that is 43.5 divided by h to the power 0.9, and then we can see how we can automatically calculate the wind load on the various structural elements. So first of all, I will like to model a basic RCC building for your better understanding. So enter units meter kilonewton and joint coordinates 1, 0 and 0. So press Shift plus K option on your keyboard, select the nodes cursor here, and select the press Ctrl C and Ctrl V option on your keyboard. Select X as 6 meter. Select both the nodes and then select translational repeat along Z, and default step spacing as 6 meter and number of steps as 4. Select the option of link steps. Select this option of adding beam here. Select all the beams and then select translation and repeat along Y direction, and the spacing is 4 meter. Select the number of steps as 5. You can select link steps option. And to make the structure somewhat more interesting, what we can do is that we can go to this view from plus Y, select all the beams here, and then select translational repeat along XS, and default step spacing is 6 meters. And we don't need to select link steps here, and we can select number of steps as 2. Go to this view from plus Z and then some randomly delete a structure from here. So right now we have a L-shaped building, and we can go to this view and delete all the beams here. So now we have a simple RCC structure, and we can go to general and support and then create, fixed, add, and then we can select the supports cursor here. I'm making these simple processes go fast, as it has already been explained many times in the previous lectures also. So some steps I will do very fast, and some steps which I think we are doing for the first time, then I will do it slow. So coming back to the this property option here, we can go to define rectangle. We can select the size of columns as 0.5 by 0.5, and the size of the beam as 300 by 600. If we are selecting YD is equal to 0.6, it means the depth of the beam is 0.6, not width of the beam. Width of the beam is this. So the width of the beam is 300 and the depth of the beam is 600 mm. Left click on add and close here. And if we want to make a single size column along the whole structure, then what we can do is that we can go to select beams parallel to y-axis. So all the columns will be selected, and this option is already selected, so we can left click on assign and guess. So now with this simple option we can define 500 by 500 mm columns to the whole structure. And after that, if we want to define whole beams, what we can do is that either we can just draw these rectangles here and select all the beams, or what we can do is that we can go to select beams parallel to X, select beams parallel to Z. So with the simple option we can easily select all the beams in our structure. And after that, coming to our main point, that is load and definition and wind definition. So before that, before we enter the data, we should be familiar with all of the options, that is the height of the structure, the width of the structure, and the length of the structure. So our building is basically 24 meter by 18 meter and the height of the building is 20 meter. So if we want to calculate the natural frequency of the structure for concrete for mortar resisting frame is 43.5 divided by h to the power 0.9. So we select the 20 to the power 0.9. So 43.5 divided by 14.83. So the natural frequency of the structure is approximately 2.93 cycles per second or hertz. So left click on add here, and then again left click on add, then left click here, and then again left click on add. So here we need to select calculate as per ASCE. There's one more thing that you should know. We can also generate loadings as per the Russian standards. Here this SNIP 2.017 2011 is a Russian standard. So with this simple option, we can just enter the data here, and then STAAD will automatically calculate the wind loading. If you are going as per the European or American or the Indian standards, then you need to enter the value manually here. There is no option to automatically calculate the wind load as per the Indian or European standards. So if you are like from India, then you need to calculate as per the IS 875 Part-3, and there's a table in which it shows how to calculate the various intensities for different heights. But coming back to our topic, that is as per ASCE 7. So here we can select A 2010 building classification category is category 2. Yeah, for basic wind speed. Basic wind speed is also given in ASCE 7 2016, and I must say that in all these versions for different cities, there maybe it has happened that the wind speed has been revised. So I will advise you to always refer the latest version for the calculation of wind speed. If you are working as per the American standards and you are working in the American continent itself, or you need to design structures for any American city, then I will advise you to go to this ATC hazards by location website. The specialty of this website is that it automatically gives you the wind load, snow load, tornado design wind speed, and seismic loads as per your location or as per your pin code. So you don't need to go to the standards again and study the contours and find out the wind speed. You can just enter the address, or you can enter the coordinate here, and then automatically it will tell you what is the data for the wind, snow, tornado, and seismic. So let us say if we want to find the wind speed for Los Angeles. So here we can enter Los Angeles. So here it is giving us the MRI, that is mean recurrence interval. So if we want to see the contours as per the American standards also, so here we can left click here. So it will also show us the contours for the speeds for the various cities. So here you can see that the speed is approximately in between the 66 miles per hour. And if we want to go for the 10-year period, but if we want to go for the 50-year return period, then the speed is approximately 77 miles per hour. And this is as per the ASCE 7 2016, whereas in ASCE 7 2010, so it was not guiding us about that, and it was like specifying for the authority for having special jurisdiction. Let us say if we want to calculate the speed for Las Vegas. So here it is showing us that for Las Vegas, the height is approximately 2006 feet, and the return for 50-year return period mean recurrence interval wind speed is, and that is MRI, 80 miles per hour. Whereas as I was telling you earlier that for ASCE 7 2010, the same wind speed was 90 miles per hour, and it has been now decreased to 80 miles per hour. And ASCE 7 2005 also the speed was 90 miles per hour. So always refer the latest standards for the results. So let us say if we want to calculate the snow loading also, then the snow load is approximately only 5 pounds per square feet. And tornado, let us check the tornado wind speed is approximately 130 miles per hour. And for seismic also, if we select the risk category as 2 and site class as let us say D, then it will show us the value of SS and S1 parameters. That is, SS is approximately 0.586 and S1 is 0.192. The 0.2 second period and 1 second period. MC, that is maximum considered earthquake, and it is also showing us the various other parameters also. This is the horizontal response spectra for MC, and this is the horizontal response spectra for design horizontal spectra. So with this option, all these options, you can see that it is reducing your work a lot and providing us an exact location by location the value of wind speed, snow speed, tornado speed and seismic wind speed. So let us say if we want to go with this 80 miles per hour and this 50-year time period, ignoring the tornado wind speed which is very high, that is of 130 miles per hour. So if we let us say if we want to go with this 80 miles per hour wind speed, so we can enter basic wind speed as 80 miles per hour, exposure category as B, structure type as this is a simple RCC building, so we go ahead with building structures only. Considering it is over a plain land, left click on apply. After that we left click on main building data. So when we open the main building data, here you will see the various options, that is building height, building length along the direction of wind, building length normal to direction of wind, building natural frequency, and building damping ratio. So if we are considering windward loading, and in this case we will consider the partially enclosed, so what we need to do is that we need to first of all enter the data here. So please select the correct units as meter. Building height is approximately 20 meters, building length is 18, and building length normal to direction of wind is 24. Building natural frequency we can enter it as 2.93 Hz as we have calculated with the help of the formula given in the ASCE 7/2016, and building damping ratio we can take it as 0.05. Consider the building, let us say if we consider it as enclosed building, so left click on apply, and after that we can go ahead with building design pressure option. So in the building design pressure option you will find further various options, that is windward, leeward, sidewall, use G, use CP and use GCPI. Now the thing is, the most important concept that you need to understand while we are generating the wind loads as per the American standards in the STAAD itself is that you need to define 6 type of wind definitions. So there shall be type 1, type 2, 3, 4, 5, 6 different type of definitions. The number 1 definition shall be type 1 windward with plus GCPI. I am repeating the term, type 1 windward and plus GCPI. So we tick this option here, and then if you remember the code for this enclosed building, the GCPI value was plus minus 0.18. So first of all we take it as windward and plus GCPI and left click on apply. So left click on OK option, and here you can see that the STAAD has automatically generated the wind loads for various heights. So the maximum value is 0.288 kN per meter square, which is, I must say, a very minimum value. So left click on add here, and then factor we can add it as 1. So this was the thing that I had done, that I had named the first wind definition as type 1 windward and plus GCPI. That you can do it on your own. So this I am not showing in the video. After that we again name the second type as windward and minus GCPI, and this we will enter it as type 2. So left click on add here. Our third definition shall be for leeward plus GCPI Fourth shall be leeward minus GCPI. Fifth shall be sidewall plus GCPI. And sixth shall be sidewall with minus GCPI. So exposure we can assign to view here. And type 2 windward minus GCPI, the option shall be same for both the options. So we consider it as basic wind speed as 80 again. Left click on apply. Building height we consider it again in meters only. Building height as 20. Length along the direction of wind as 18 and normal to direction of wind as 24. The frequency shall be 2.93. Building damping ratio shall be 0.05 and the building shall be enclosed only. So left click on apply here, and building design pressure shall be windward and minus GCPI. So left click on apply here and then left click again on OK. So now the maximum intensity is coming out to approximately 0.498 kilonewton per meter square, and exposure factor shall be 1 only. So this we can assign to view again. After that we will take it as the leeward plus GCPI and leeward minus GCPI. So again we repeat the procedure here. So we enter the basic wind speed as 80 miles per hour, exposure category is B again, and building structures, left click on apply. And after that we go to main building data here and we enter the units as meter again. Building height as 20 meters, building length along the direction of wind as 18, normal to direction of wind as 24 meter, frequency is 2.93, damping ratio is 0.05 and enclosed building. Left click on apply again, and building design pressure is leeward with plus GCPI. So here we can see that automatically only 2 options are available. So left click on OK, and then again left click on add here, factor as 1. So again we go for leeward minus GCPI. Left click on OK, and then again left click on add here. Enter the factor as 1 and close. After that we have this option of sidewall, that is when we want to consider the wind that shall be acting on both the faces here. So we left click on add here. Basic wind speed as 80 miles per hour. So now we have generated 6 type of different definitions, that is windward plus GCPI, windward minus GCPI, leeward plus GCPI and leeward minus GCPI, sidewall plus GCPI and sidewall minus GCPI. So now we will generate the 2 load cases. That is, the number 1 load case shall be, first of all we need to enter obviously dead load and live load. After that we need to select wind here, and then we can select wind load with plus GCPI. And then second shall be wind load with minus GCPI. So for with the plus GCPI, we left click on add here, and then we left click on wind load. So here we can see that all 6 different types of definitions are available here. So if we first of all want to go ahead with options with plus GCPI, we go ahead with type 1 wind speed, and expose the exposed surface and direction as X and windward face, the factor as 1. So here we can see that the sign loading convention is given here, and after that we need to enter the range also. So as we want to go ahead with the whole structure, so we can left click on add here. And the thing is that here the software is showing us the different contours for the loading. So if we want to switch on to some other this sign parameters, like, so we need to left click on labels. So here we will see that we can left click on loading values and display, untick this area. So this is the wind load that has been generated. So here we can see that the 1.711 kilonewton loading is being applied on this joint here. And if we want to display the wind load contributory area also, then this is the option. And if we want to decrease the scale, so we can just apply here. So this is the value that has been generated on the junctions here. So this was just one type of wind definition. Then we need to left click again on add here. So we selected as type 2 here. So we first of all, in this case, we need to select, as we are selecting only plus GCPI, and type 2 was minus GCPI, so we need to select third wind definition here. We need to go ahead with the minus X, that is leeward sidewall face, and factor as 1, and left click on add here. So here we can see that the loading has now been applied on the leeward face by itself. So after that, when we left click again on add here, then again wind load. So now we need to select the 5th, that is sidewall loading case here, and then we need to select the minus Z option here and factor as plus 1. So left click on add here. So now you can see that automatically it has generated the wind load on the sidewall, and then again we the last option should be wind load, type as 5, the direction is minus Z, and the factor is minus 1. So left click again on add here. So here you can see that automatically the wind load has been generated on this point. So if we press shift plus V option on a keyboard, so here you can see that on each and every node, the STAAD has automatically calculated the wind load, which otherwise if we want to calculate manually, it would have been very cumbersome and very much time consuming. So just to decrease the calculation time, the STAAD has offered this beautiful arrangement in which we can calculate the wind load for various directions and for various exposures and for various, that is both plus GCPI and minus GCPI also. So now we have generated the four types of wind loads for plus GCPI. Similarly, we need to do the action again for minus GCPI. So we left click on add again, go to wind load here, go to as type 2 regular, select X here and then 1, left click on add and close. So now we can see that the similar procedure has been repeated again, obviously with minus GCPI. Again we select as type 4, minus 6 leeward sidewall face, left click again and add here. Then again we go with the sidewall loading also. Enter the factor as +1. And then we again repeat the same procedure with -1. So here we can see that again the STAAD has automatically calculated all the wind loads for minus GCPI also. So this was just a short exercise to make you familiar with how we can calculate the wind loads as per the American standards. What are the various codal guidelines which guides us on how to calculate the wind load for main wind force assisting systems, that is MWFRS, and what are the values for various types of openings, that is partially enclosed, enclosed and open structures, and how we need to take the values for plus GCPI also and minus GCPI also as per the codal guidelines. So this was just a standard set of procedures that we need to follow if we are considering this simple RCC building and we need to calculate the wind loads for that structure.